Alrighty, welcome back. Today we build upon more of what we've been talking about. I think we ended the last lecture kind of looking at different kinds of forces. We looked at the contact force between surfaces, sometimes called the normal force. We looked at the gravitational force, which also relates to your weight. And we looked at a couple examples in 1D and 2D about applying Newton's laws. Let's do a little bit more of the same today. Well, here's a question we'll use to start with. You're standing on a bathroom scale in an elevator, for whatever reason, which is accelerating upward, e.g. maybe right after when the elevator starts moving up, that jolt you feel when it starts to move up. Does the scale read less than, equal to, or greater than mg, your weight? So again, how would we do this? I want to study my motion. So I will start by drawing a box around me, which I will call the system. And I will identify all the contact forces on me. I'm in contact with the ground or the scale, so I'll call that the bathroom scale, perhaps. Then I am not in contact with anything else, but of course gravity is pulling me down towards the ground. Now you might think the elevator is accelerating upwards. We have to take that into account somehow, and we will. But it is not through any sort of force. The cable that's attached to the elevator is what is pulling on the elevator and causing the elevator to accelerate upwards, but that is not what is causing me to accelerate upwards. Next step, free body diagram. Maybe I'll have up as positive. So I have gravity, which of course always points down, Fg. And I am in contact with the surface of the floor. There is some sort of surface force, which in this case I'm calling the force of the bathroom scale. And that is whatever that force is what would be read off the bathroom scale. So if I had to assign some values, the bathroom scale I might say is plus F, plus because it's pointing upward. Fg I might say is minus mg, minus because it's pointing downward. And I also know that I am accelerating upwards. So maybe I'll just write that as plus A. The plus sign, of course, because I'm accelerating upwards. Next step would be my general statement of Newton's second law. All the forces acting on me equals my mass times the resulting acceleration I experience. In this case, the acceleration on the right-hand side is not zero. We know that I am accelerating upward in this elevator, therefore I do have some sort of acceleration on the right-hand side. I'll start by the sum of the forces, so the bathroom scale plus the gravitational force equals my mass times my acceleration. All plus signs. And now I will add in the actual expressions I have for each of these forces, including the pluses and minuses based on my coordinate system. So the bathroom scale is plus F, the gravitational force is minus mg, and then this is m, and I'll just write A, which A itself is assumed to be positive in this case. And what do we get? We get the bathroom scale is ma plus mg, or m of a plus g, which is, since a was positive, is indeed greater than mg, your weight. The bathroom scale would read a larger number than my weight. And you can actually do this experiment if you wanted to. That is also why you feel kind of jolted to the ground when the elevator just starts to go up. And then if we were to do this problem but it was accelerating downward, when the elevator just starts moving down, that's when you feel yourself going to float a little bit. You feel a little bit lighter as you begin to accelerate downward. Now, physically, we could think, why does the weight have to be greater than, or why does the force from the bathroom scale have to be greater than your weight? The bathroom scale in this case, or the floor of the elevator, that is what is causing you to accelerate. It is the floor pushing on you, and it is pushing you upward with some amount of force that causes you to accelerate against gravity in the upward direction. While that cable might be what accelerates the elevator itself upward, which includes the floor, the fact that you are in contact with the floor is what is pushing you upward. It is the floor that is causing you to accelerate into, up. How about a 2D example? Suppose you have some box and there are two people pushing on it. There's someone who is pushing on it horizontally to the left. And then there is some giant that is pushing on the box at some angle on the box to the right. Let's suppose each pushes with, let's say, 10 newtons of force. But the giant pushes at a 60-degree angle from the horizontal. If the mass of the box is 5 kilograms, what is the acceleration? Both magnitude and direction. And then also, if the box were on a scale, is it less than, equal to, or greater than mg? Now, intuitively, you should make an educated guess as to what these are going to be. The value for A might be hard, but you could reason out whether it should move to the left or to the right based on what I've told you. You should also, based on the direction of the forces, be able to tell whether you expect the box to be less than, equal to, or greater than the mass of the box times little g. All right, again, here we go. There is my system. The system appears to be in contact with the giant, the person, the ground, and then, of course, gravity. So I should expect that there are 4 forces at play here. So my free body diagram, right, there's the force due to gravity, the person pushing to the left, we'll call that F person. The giant that is kind of pushing at an angle, I guess G is already taken, so we'll, GI. And then it is touching the ground, so it's in contact with the surface of the ground. So I expect there to be some sort of surface force. Which ground also starts with G. We'll call that F sub S. Or if you want to call it the normal force, we could call it the normal force. But I refuse. And we are also told this angle here is 60 degrees. Though I did not draw it very well, if that is 60 degrees. All right, and let's make some choices. Let's have to the right be positive and up be positive. So in this case, the force from the person would be, it's purely horizontal. So if I were to write this as a vector, I'd write this maybe as minus 10 newtons, comma 0 newtons. He's pointing to the left in the horizontal direction, and he's not pointing up or down. The gravitational force only points in the vertical direction, so it's not horizontal. And then it's minus mg in the vertical direction. I should give a value for 10 newtons, so I don't have to have a bunch of tens. Let me get rid of that. And I'll call this Fp for F push, which is 10 newtons. Again, I prefer symbols rather than numbers until the very end. There is the surface, which I expect to act only in the horizontal direction. And maybe then I will allow us use n, which I assume this is positive, so that n is a positive number, and what we'll call the surface force or the normal force. And then there is the giant, which is pointing down and to the right. So I expect the horizontal component to be positive and the vertical component to be negative. Now, if I look at the diagram, it looks like I've drawn the force like this, where this is some angle. So again, I could break this into a horizontal and a vertical component. There is this part here, which is the vertical. There's this part here, which is the horizontal. The horizontal looks like it's just going to be F push cosine of theta. And then I'll manually put that plus sign in front to remind myself that's pointing to the right. For the vertical, the magnitude is going to be F push sine theta, but then I can throw a negative sign because it's pointing downward. So then this would be F push, or 10 newtons, cosine of 60 degrees, which is a half, and then negative F push sine of 60 degrees, or root 3 over 2. We will eventually need a calculator, so I will get that ready. All right, so this is Fp divided by 2, and then this is root 3 Fp divided by 2. All right, now we have components for all of the forces in this problem. We could again start super general. All the forces acting on the box equals the box's mass times the box's acceleration, which happens as a result of these forces. But here we have both the x direction and the y direction both matter in this case because there are forces in both. This is not a 1D problem. So I could, like we've done before, I could break this up into the x direction, and then I could break this up into the y direction. So in the x direction, I could say the sum of the forces in the x direction equals the mass of the box times the acceleration in the x direction. And in the y direction, the sum of the forces in the y direction equals the mass of the box times the acceleration in the y direction. And now I have 4 forces, so I can just add up all of them. So I have the force from, what did I call it? I guess from the person. Oh, I guess I'm using F sub p twice. I'm so sorry. We'll call this PU for push. So that's PU. So we have force from the little person, we have the force from the giant, we have the force from gravity, we have the force from the surface. All equals the mass, and we're looking at, in this case, the x component of each of these vectors. And that equals the mass of the object, the box, times the resulting acceleration in the x direction. And then similarly for the y. Now, do I need all four of these forces? I don't, because some of them don't operate in the horizontal direction. For example, gravity and surface force. Notice that in the vectors above, both of them are 0 in the x direction. So I do not have to worry about what's going on there. So let's see. From person 1, we said that that was negative pu. Then gravity has nothing, surface force has nothing, and then the giant is pushing with 1/2 pu. Plus 1/2. Now notice the plus and the minus sign have meaning at this point. Equals 10 mass. Equals mass of the acceleration times the acceleration. Mass times the acceleration in the x direction. This left-hand side is just 1/2 pu, or negative 5 newtons, equals the mass of the box times its horizontal acceleration. The mass of the box was 5 kilograms, so then this is minus 1 meter per second squared, equals the acceleration in the x direction. It is negative, therefore it points to the left, and is moving to the left. Now in the y direction, again, we can look at all four forces. Not all of them have a component in the y direction. Gravity was minus mg. The surface was n. And then we also had a minus √3/2 fpu equals the mass of the box times the acceleration in the y direction. But now we can take this a step further and ask ourselves, is the box lifting off the ground? No. Is the box sinking into the ground? Being absorbed by the ground? No. So in this case, the acceleration in the y direction is 0. Its motion is not changing in the vertical direction, else it would start to move either up or down. In this case, the idea is that the box is just sliding across the floor. So in this case, we could then solve for, say, the contact force, which is the only thing we don't know in this problem. You should notice that you get mg plus √3/2 fpu. I guess I could plug in numbers if I wanted to, but really the only thing I could take away from this is that this is clearly greater than mg. And as a result, the scale underneath that box would read greater than the weight of the box. And again, hopefully that's more straightforward at this point, because this is, again, kind of an instance where you're standing on a scale and someone is pushing you down towards the ground. Obviously, the scale responds, has to push back harder, the reading on the scale goes up. Your book actually does not talk about springs in this chapter, which is an interesting change, I think. Or rather, I remember when I used this book, not this edition, of course, but an earlier edition of the same book when I took undergraduate physics, that they also would talk about the spring force. And we've already seen springs a lot. I actually really like springs because I think they're a good visual way of imagining what forces are doing. Because you can see there's some visual component where you can see there's a tendency for the spring to return back to its original shape and size. In this case, the spring was stretched and it wanted to return back, or in this case, where you compress the spring and it returns back once the contact force disappears. What's also really nice about springs is that for idealized springs, which are most springs, as long as you don't stretch or compress them too much, there's a very simple relationship between the amount of force they are exerting and how much it is compressed or stretched. You could imagine measuring that in some way, the amount of stretching or compression. in this case, it's kind of hard to see, but there are little tick marks, that correspond to, in this case, it says how many newtons of force are being applied. But you can imagine the way you could do that is that you could move it down or stretch the spring by some amount, by different amounts, by measuring kind of, here's where it started. So this tick mark here is kind of representing where it started. And then if it got stretched by this amount, say, then you could say, okay, I could take a ruler, which I don't think I have one at this stage, and I just dumped my desk all over the floor. Awesome. Or you could take a ruler and you could measure, what distance this corresponds to. And you could say, okay, when the spring was stretched by that amount, how much force was being applied? And then how does it change as you stretch it by different amounts? Or how does it change as you compress the spring by different amounts? All right, 1 second. And the simple relationship that gives you these relationship, or the simple relationship between the amount of force and the amount of compression, is now what's known as Hooke's law for ideal springs. For ideal springs, the relationship between the force the spring exerts and the amount the spring is stretched or compressed is given by Hooke's law. This is the same Robert Hooke, actually, if you remember from a few lectures ago. That was Newton's arch nemesis. So the expression is that the force from the spring is negative K, and I'll call it delta S. So the K is the spring constant. So it's telling you how, for a given amount of stretch or compression, how much force would you expect. For this particular very thick spring, it has a very large spring constant because it's very hard for me to compress the spring by a good amount. Versus with this one, it's very easy for me to just click and pull and stretch the spring by quite a large amount. This would have a low spring constant. Units are then newtons over meters, for example. Why is that the unit? Because I've not defined the other variable yet. But this other variable, delta S, is the length the spring has stretched or compressed. Apologize for my penmanship there. And this stretch or compression can be positive or negative. It ultimately depends on your coordinate system. If you have a delta S that's positive, that means that the spring was stretched or compressed in the positive direction. So if positive is that way, this, me pulling it out this way, would be a positive delta S. And then as a result, if you look at the formula for the force, if delta S is positive, K is always positive, the force is negative. That means the force is pointing to the left. There's a tendency, the spring wants to return back from where it came from. In contrast, right, similarly, if this direction is positive, and I compress the spring from its original position, I have moved the location about this end of the spring. I've moved the location towards, I guess, my left. I'm not sure how it's appearing in the video. It might be flipped. I'm moving in this direction, which was the negative direction. So delta S is negative. Negative K delta S is therefore positive. The force is then pointing in the positive direction. The spring wants to return back in the other direction. Right. The takeaway is that the force wants to return the spring to its original length. Right, and the thing you have to be careful about is that sometimes the books and whatnot will just write the spring force as, say, minus kx. And that's fine, but there are assumptions built into that expression. When they say negative kx, what they mean is that the spring is at its state of not being stretched or compressed at all at x equals 0. So then if x is 2, that means it's been pulled in the positive direction, or if x is negative 1, it means it might have been stretched or compressed in the negative direction from 0. So just be careful about that. There can be assumptions sometimes built into when the formula is written like that. That's why I like writing it as delta S, because I have to think about what's going on. There's something physical here. It's a spring. And I have to think that is the spring being stretched or compressed? And there, with that in mind, I can think about the direction of the force. For example, suppose I have a spring that is hanging from the ceiling and is attached to a box. The box has some mass m. The spring has some spring constant k. And I could ask, how much does the spring compress if the box is stationary? Box is stationary. What length does the spring stretch or compress? Now, your intuition probably is probably correct to think that what's going to happen, of course, is that the spring is going to stretch as a result. If the object, in this case the apple, is not moving, the spring is doing something to balance gravity. If it's just hanging in the air, gravity has not turned off. Gravity is still trying to pull the apple downward, but if it's not moving, that means something must be balancing the gravitational force, which in this case is the spring, which you can see stretches as a result. The spring then is exerting a force on the apple, or in this case on the string connected to the apple, which is holding the apple aloft. So again, we're studying the mass. That's my system. My free body diagram might look something like this. There's the gravitational force, and then I imagine that there's some spring force pulling back up on the box. I could define up as positive, in which case the spring force is written as, the formula gives it as minus k delta, and I'll write delta y in this case, since this is the vertical direction. We're doing everything in the vertical direction. You might say, wait, you said up is positive. Careful. This negative sign, right here, that is part of the formula for the spring force. It's always negative k delta s, or delta y in this case. But how do you reconcile that? Delta y can be positive or negative. So if you are thinking, well, the force has to be pointing upward, and we have this negative sign you just wrote down, the only way to reconcile that is if delta y is negative. which would suggest that the spring is stretched downward, which I think your intuition is saying is what actually happens. So we shall see. The math will justify what we are doing here. And then the gravitational force is minus mg. I almost made the mistake myself. Minus mg, in this case, the minus sign because I'm saying something about the coordinate system. M is always positive. G is always positive. So this minus sign is saying that the force points down. And again, just to repeat, for the spring force minus k delta y, k is always positive, but delta y can be both positive or negative. So the negative sign in front of that is just because it's part of the formula. The negative sign is saying that the force always is in the opposite direction as the stretch or compress. If you stretch it in the positive direction, the force wants to take it back to the negative direction. If you compress or stretch it in the negative direction, the force wants to take it back to the positive direction. And what else do we know? We know the object is not moving, so that the acceleration therefore must be 0 in the y direction. And we're off. Sum of the forces equals the mass of the object times its acceleration. There's only two forces here, and they're both vertical, so I'll dispose with the vectors. So the sum of the two forces equals the mass times acceleration, but we said that is 0. Now we plug in, we got negative mg minus k delta y equals 0. Which implies delta y is negative mg over k. M is always positive, g is always positive, k is always positive, but there's that negative sign, so that this entire thing is less than 0. So the spring stretches down. Again, kind of as was expected. The apple causes it to stretch downward, which in this particular coordinate system was the negative direction. We will see the spring force in much more detail later on when we do oscillations. But for now, what's nice about the spring force is that it can be a helpful way of understanding what's going on with inanimate objects like ropes, tables, example. Hooke's law is actually a quite useful and ubiquitous law that comes up a lot in physics. Most motions can be understood, for solid objects, can be understood via Hooke's law. When you punch a wall, for example, if you were so inclined, the wall itself might not necessarily change shape when you hit the wall. It might just still remain a flat surface. But actually, when you are in contact with the wall, when your hand is touching the wall, it doesn't stay perfectly rigid. It actually bends inward a little bit when you punch the wall, and then when your hand gets taken away, often it just returns back, it restores itself back to its original flat wall. Unless, of course, you punch way too hard and leave a dent in the wall. I think I had suggested you could do this, where you could stand on a table with a laser pointer, and you'll notice that the laser pointer light will bend and point somewhere else. The table itself is bending. Like a heavy bookshelf, the inanimate wood of the bookshelf does bend a little bit. But if you were to then take all the books off, the bookshelf would go back and restore itself to being flat. That restoration is, again, if you were to model it, you would model it as that restoration force that is holding up all those books and causing the bookshelf to bend can be modeled as negative some constant times delta y, or delta, how much it's being compressed or stretched. In the case of a bookshelf, how much it's bending. So this kind of restoring force, it's sometimes called, this negative, a constant, times how much it's being stretched or pulled. That sort of restoring force pops up a lot in physics. And again, like for the chemists, in the audience, when I look at with a table is a solid. I can press down on the table and my hand doesn't sink into the table, or I don't sink into the chair. The chair stops me from falling to the ground. And at a microscopic level, we could look into it and we would see that there's all these various molecules, and they all have molecular bonds with one another. They might be sharing electrons, there might be ionic bonds, there might be other various bonds that are holding together all the molecules that make a solid. And if you were to press down on, say, the table or the chair, what you are doing is you are compressing and causing a slight bend in all of those individual little atoms and molecules. All the bonds are getting pressed down a little bit, kind of like a spring being stretched. And so what is really happening when I'm sitting in this chair is you can imagine that all the individual molecules that make up the solid of this chair cushion, they're all acting like billions and billions of little springs that are pushing back up on me. And that overall contact force is really just the result of maybe trillions of tiny little molecular springs pushing back up on me and causing a force that holds me up. When I press down on a table, where I press down, those molecules bend ever so slightly. And that bending, it wants to restore back, it wants to snap back to where it was, like how a spring wants to snap back once I let go of it. That compression acts essentially like a bunch of tiny billions and billions of molecular little springs pushing back on me. Similarly with rope or cord or whatnot, when we could talk about tension, you can imagine I could tie this not to a ball, but I could tie a string to the wall, like say wrap it around my door handle. And then I could wrap the other part of the rope around my hand. And you can imagine I could pull on the rope. And maybe if I pull hard enough, I could say pull the door open, or I could, pull something off. If it was a hook on the wall and I pulled hard enough, I might be able to eventually pull the hook and part of the wall off the wall entirely. And you might think, what's going on? If we were to do a free body diagram, my hand is touching the rope. We can even draw that real quick. Here's the wall. Here's a string that's attached to the wall. And I'm pulling on the rope. And I might pull eventually hard enough so that I pull the hook, I pull the door open, I pull part of the wall off the wall. So clearly what I'm doing over here on the rope is having some influence on what's going on the other side of the rope. And again, what's happening is if I were to analyze, say, if my system were, say, the part of the rope that is right next to my hand, that free body diagram might look something like I'm pulling on the rope in one direction, force me. But if I'm pulling on the rope and the rope itself is not moving, right? This rope, I'm pulling on both sides of the rope actually right now, and the rope is very taut. But the rope itself is not moving. There's no overall velocity of the rope. So I would say the velocity is 0. It's not changing. The acceleration must therefore be 0. There must therefore be some sort of balance, which I'll call T, the tension in the rope that is balancing off the fact that I'm pulling on the rope to one particular side, but the rope itself is not moving. The rope itself, there must be some sort of restoring force that it's having to resist the fact I'm pulling on the rope. And again, what you're doing is you're taking all the little individual molecules that make up the rope, and all those bonds are being stretched out a little bit, but they don't want to do that. They want to click back to where they were. So again, you kind of think of the rope as billions of little springs that I'm stretching a bunch of little springs. And when they all work together, they essentially have a very, very large spring constant because the rope itself does not really change length that much as I pull. But you can think of it as just a bunch of springs pulling back on me. And you can kind of see this too with some rope, like when you stretch, you know, I'm not really seeing it with this one. But for some ropes, you can, you know, when you stretch it, sometimes you see it kind of thin out a little bit. You can actually see it change shape a little bit. And when we do Newton's third law, we'll talk a little bit more about this. But again, for now, let me just say that you can think of a rope as, you know, many little springs in a line. All adding up together. To create tension. In that tension, we will see when we do Newton's third law, you could actually prove this. That tension is uniform throughout the spring. Or, sorry, the rope. Tension The tension is uniform throughout the spring, throughout the rope, pointing in both directions. You know, if I look at an individual little piece of the rope in the center, you know, it is being pulled both towards the left and towards the right by the pieces of the rope that are right next to it. You know, again, this would amount to me doing, say, a little free body diagram on this part of the rope, that little chunk of rope. And it's touching a little bit of rope to the left, it's touching a little bit of rope to the right. Each of those are pulling on the rope, you know, with some tension. And that tension becomes uniformly distributed throughout the rope, except at the end points where it actually can act on other objects that is not the rope. So I could write except at the end points. And there the tension acts in one particular direction. It acts along the rope, away from the object it's attached to. So in the case of the wall, right, the free body diagram here for the wall in that case would feel a tension force that is pulling to the right along the rope. You know, in the case of over here where I am pulling on the rope, a free body diagram there would, you know, for me, if this were a free body diagram for me, I would feel a tension pulling me to the left. And again, that in the fact that there are these kind of the symmetry throughout the rope, but not at the endpoints. Essentially, the rope will act as, you know, as long as the rope is taut. If the rope is not, you know, like this, then obviously anything I do over here is not necessarily directly transmitted to the other side. But essentially the taut rope acts as a way that forces of what's going on over here gets transmitted to the other side through all those little springs that make up the rope. For example, right, suppose there is a nail. Suppose there are two nails. And across the nails is, say, a piece of rope. There's some box on one, that the rope is attached to one box that has mass M1. And then maybe over here, the rope is attached to another box that has mass M2. And these are smooth ropes, and it's a smooth rope, and the nails are smooth, so let's not worry about friction or anything like that. And I could just ask, what sort of tension is being felt by the rope? Are the objects moving at all? How can I analyze this? Let's take the case first. Let's take case 1 where M1 equals M2. So we'll call that A. There, your intuition might give you a sense of what's going to happen. I have two equal objects on both sides of the rope. They are both hanging. You might imagine that in that case, the rope, nothing is going to move. They're in some sort of balance with one another. And we could see if that is indeed the case. So in these cases, this is an example where we have multiple objects. Before we were just analyzing a single object where there could be multiple forces. Now it might be the case where we have to think about multiple objects that have some sort of force that is potentially connecting the two. So let's look at M1. It is in contact with the rope, and then there's gravity. If I look at M2, it is again in contact with the rope, and there's gravity. So for M1, I might say that gravity is pointing downward, and then the tension in the rope is pointing upward. The force is along the direction of the rope, that the object is connected to. For M2, I might say the same thing. Sorry. And here I'm making the assumption, which for now you'll just have to take, that the tension becomes uniform throughout the rope, as long as it's taut. It's a taut rope. The tension throughout the entire rope is completely uniform. And if M1 equals M2, then it makes sense that both of these cases are going to have the exact same expression for Newton's law of motion. F equals ma is going to be the same for both. Both have the same forces acting on them, so they are as a result going to have the same acceleration. I could write that down. Let's see. Shall we define up as positive? Sure. So they both are going to have something that looks like this for both of them. And maybe they have different accelerations, I don't know. So I'll put A1 and A2. But I know they both have the same tension, and they're both the same mass, so I'm just writing M instead of M1, M2. All right. But in this case, notice I could write M times A1 equals T minus mg. But T minus mg also equals MA2. Essentially that's this, and then that is this. So they're connected by their forces. So in this case MA1 equals MA2, or A1 equals A2. And in this case, I claim that the only possible answer is that they're both equal to 0. You might think, why can't they both be positive? Or both be negative? Maybe they're both 1 meter per second squared. But then you have to think about what that means given the picture you drew. If they were both 1 meter per second squared, that would mean that both of the boxes are accelerating upwards with time. If that were the case, let's just take that as a given. Let's assume that's happening, though it's kind of silly to imagine. If that were the case, that the rope was somehow bringing both boxes into the air, clearly the rope would not remain taut, or perfectly stiff that entire time. Let's see. Let me attach my apple to the string. In the case where they are both moving in the same direction, for example, here. If they were both moving, get rid of this. If they were both moving upward, here gravity's pulling them down. Clearly, the strings are remaining taut. If they both were accelerating upwards, clearly the string begins to slack. The tension would actually go away. There's no tension right now because the string is not being stretched in any way. Here, there's tension. It is, stiff. There is a force that is resisting the fact that these are not just continuing to fall towards the ground. This, there is no tension. There is no actual force from the rope anymore in this case because it's not stiff. In this case, again, it is. So then I would say that just sounds like nonsense. That would be a contradiction. There would therefore be no tension if that were the case, if they were both moving up. If they both were moving down, obviously that would be very problematic for the rope because the rope, which is taut and not changing shape, if they both were moving down, then something's going to happen. Likely the rope is going to snap if that's the case. And then again, the tension force would disappear. So it doesn't make sense that you would be able to justify it that way. So in this case, I would say the only possibility is that A1 equals A2, which is 0. They don't move at all. You can ask, what if M1 is bigger than M2? In this case, the free body diagrams still look the same, but now I have to be careful about my symbols. So then these are Newton's laws written down for box 1 and box 2. But now their masses are different, and we have to think about what happens with the accelerations. But they're still connected by the same rope, and that tension is uniform throughout the rope. So there is that one thing that connects them, the tension. They both have the same value for the tension. So in this case, I could say T is M1 A1 plus G, and here T is M2 A2 plus G. Or if I wanted to connect them, they're both equal to T, so I could say M1 A1 plus G equals M2 A2 plus G. Which gives us some relationship between the two accelerations. But it doesn't give us a value for them. Here's the insight that usually is the case when you're dealing with ropes. Well, now I've created a knot. In the case of ropes where you have the shared tension connecting two objects, the fact that the rope is not changing shape remains the same length as the object. In this case, there's one object here which is heavier than this one, which is nothing. If I were to let it go, obviously it accelerates downward. And the one that is more massive seems to go down, while the one that is less massive, in this case nothing, accelerates upward. And again, there is a relationship between the acceleration downward for this guy and the acceleration upward for the other one, in that they're equal and opposite. You might think, why is that the case? Suppose they weren't. Suppose they were not equal and opposite. In that case, that would mean, for example, the heavier ball is accelerating towards the ground faster than the other object, M2 in this case, is accelerating upwards. And you can think, what happens relatively if that were to be the case? That means the velocity is growing at a faster rate for M1 than it is for M2. A string is not going to be able to survive that sort of situation. That is saying that what's going on the left-hand side, it's plummeting downward much quicker than what's going on the right-hand side, where it's trying to accelerate upward at a slower rate. As a result, that would cause the string to get stretched more and more and eventually snap. So as is often the case when you're dealing with connected objects through strings, if the string as a result allows them to move in opposite directions, there is a connection between their accelerations, where usually their accelerations are equal but opposite in sign. And this we might call the string constraint, perhaps. Of the fact the string is not changing size, so whatever happens on one side of the string must also happen on the other, else the string would grow or compress. Right, the nice thing there is that then I can substitute that into my expression. And now I have an expression just for a sub 1, for example. So I could say this is m1 a1 plus m2 a1, if I move that to the other side. And this is m2g minus m1g. Or perhaps if I just do the algebra, it is 1 over m1 plus m2. And then this looks like it is m2 minus m1 on the top, all times g. I think who cares? Let's now, but we now have to interpret this. I said before that, what did I say? I said that m2 is less than m1. So as a result, m2 minus m1 is less than 0. As a result, if I look at the numerator, that involves m2 minus m1, that says that a1 is less than 0. That says box 1 accelerates, which direction was negative? Downward. Down. And therefore, and then by the string constraint, the acceleration of box 2 is positive or upward. And again, I think that's what you intuitively expected, even if you didn't quite follow the math, and we'll have to could revisit the problem again. You know, the more massive object goes down, accelerates downward, while the less massive object accelerates upward. All right.